Okay, welcome back to the online lecture. Now this is the second to the last week of the online lecture, so we have only 2 weeks remaining. And let's try to remember that in the spring semester, we studied the Newtonian mechanics. Everything we learned in the spring semester was about Newton. And in this semester, until last week, we studied electromagnetism and a little bit of optics. And all of them belong to classical physics. And what we are going to study in this chapter and also in the next week belongs to quantum physics, and quantum physics is a part of modern physics. In chapter 37 there is a relativity, but we are not going to study chapter 37 because actually even though relativity is also a very important part in modern physics, it will be quite difficult and not very useful in our daily life. But what we are going to study in chapter 38 and 39 is a very important quantum physics and is very important and useful in our daily life. Okay, so that's why we are studying chapter 38 and 39. Okay, let's begin. Okay, so let's make a review first. In the last lecture, we studied several different cases of diffraction and interference. First, the single wide slit, and we also studied the case of double wide slit. This double wide slit, the diffraction pattern was simply the product between the pattern from the single wide slit and also from the double narrow slit. Okay, double narrow slit is the case of the Young slit experiment. Okay. And we also learned the diffraction from grating, which is the many slit. So in this case, the position of the bright spot is equal to the position of the bright part coming from the double slit, but there was no particular minima because everywhere else was simply dark. Okay, and we also learned the diffraction from crystals, from which we studied the Bragg's law of diffraction. Okay. So in this week, we will study quantum physics. So therefore, we will begin by the introduction to quantum physics, and we will study the quantized energy of light particles. So actually, we have been studying light as a wave, but here we will study that light is also a particle. And we will also study that light waves has a linear momentum. In Newtonian physics, the linear momentum was proportional to the mass. But then light does not have a mass, so how can there be any linear momentum? Okay, it's a very strange in classical physics, but it is possible in quantum physics. Okay, and then we will also learn that electrons, which is a particle, is also a wave. So therefore, we call it matter wave. And again, it's a very strange concept if you think about classical physics, but this is how the quantum physics is. Okay, and then we will finally learn the Schrödinger's equation, from which we can study the wave properties of this matter. Okay. Now, what is quantum physics? Okay, so in order to understand what quantum physics is, we first need to understand the word quantum, or quanta in plural. This word quantum means the smallest possible amount that is associated with a certain quantity, which we can also call an elementary quantity. Okay, and examples of such things may include money or people, because, for example, we count people by 1 person, 2 persons, 3 persons, but we never count people like 1.345 person, right? Okay, so we always count them by discrete numbers, not continuous numbers. Okay. And in fact, we have already learned an example of quantum, which is an elementary charge. Okay, so in the beginning of this chapter, we learned that the amount of charge is always the elementary charge multiplied by integer. Okay, so if you remember that, this elementary charge is already something we learned about this quantum. Okay, and in classical physics, in fact, many quantities are not discrete, but continuous. And what could be the examples? For example, energy, momentum, or wavelengths, or mass. So for example, your body weight or your mass of your body actually can be any number. It doesn't have to be exactly 10 kilogram or 12 kilogram or 13 kilogram. It can be any number, right? So they are actually not quantized. They are not based on any elementary amount. But in atomic scale, interestingly, some of these quantities, actually the energy, momentum, wavelengths, and these things can be discrete and quantized. Okay, we will learn about this in detail later. Okay, and how this quantum physics actually began can be summarized in the works by two famous people. One was Max Planck, and the other was famous Albert Einstein. Okay, and in fact, it was exactly 1900, the beginning of the 20th century, when Max Planck first conjectured that the thermal radiation from a hot object, which we will call black body, was produced by oscillators of discrete energies. Okay, so discrete energy because it was expressed by the integer multiplied by certain energy, and he found that this energy, this discrete energy, was actually proportional to the frequency of the light. Okay, and we will of course discuss this a little bit more detail later. Okay, and this was the first time he had to think about the discrete energies, which is based on the elementary amount of energy. And of course, in this case, actually Planck didn't really know why the energy was discrete, but mathematically he was successful in describing something. Okay, we are going to learn it in the next slide. And let me also mention Einstein. Based on this Max Planck's work, just 5 years later, Einstein really proved that Max Planck's idea was really correct, and he even went on to really prove that light itself is quantized, and he gave it a name, photon. Okay, I think you already have heard the name photons. Okay, it was Einstein who gave the name photon. Okay, so we will study this a little bit more detail in the next slide. Okay, in this slide I'm going to explain to you how Max Planck tried to explain the thermal radiation from a hot object, and this hot object we usually call it black body. And black body, the reason why we call it black body is not because it's black. It does not reflect anything, and not reflecting simply means that it exchanges energy only by absorbing thermal radiation and also emitting the thermal radiation. Okay, and examples may be the sun or your body, which has some temperature, and then if you see any hot object, it is more or less the black body. Okay, so important thing you have to remember is that the spectrum of black body radiation depends only on its temperature. Okay, so depending on the temperature, you will see different spectrum. And of course, you don't have to know the details. Okay, I'm just trying to give you some story. And this experimental spectrum from black body was already very well known in the 19th century, and it looked like this. If you measure the spectrum as a function of wavelengths and try to measure how strong the radiation comes out, it just looked like this. So there was a peak at certain wavelengths, and if you go higher wavelengths, it was going down slowly like this, and if you go to smaller wavelengths, it was going down quickly. Okay, this was already very well known. And of course, many scientists tried to explain this phenomena, why you have this kind of curve. And of course, they tried to explain this based on their knowledge in classical physics, of course. Okay. And one example was a scientist whose name was Wien, and he tried to explain this, and this was the solution he got. And this curve looked like the green line here. As you can see, well, his solution was pretty good at small wavelengths, so it looked okay. But if you go to higher wavelengths, you can see there is a large difference between the correct solution and the solution Wien have obtained. So essentially, he was wrong. Do not memorize this. He was just wrong. Okay. And another person who tried to explain this was Rayleigh Jeans, and he got this solution, which was the blue curve. Well, he was successful in explaining the longer wavelength part here. It was pretty good, but he was very bad over here. At low wavelengths, it has to go down, but his solution was going up, so he was completely wrong at small wavelengths. Again, do not remember, he was wrong again. And Max Planck was also trying to explain this, so he made many attempts and he was just failing. And somehow he got a brilliant idea that he had to assume that the radiation, this radiation from the black body, was exchanging energies by the discrete bundles. Discrete bundles like, and then this elementary amount of discrete bundle, he assumed that this energy was proportional to the frequency of the light coming from this gamma radiation. Okay. And then whenever the two quantities are proportional to each other, you need the proportionality constant, right? So he again wrote this, the proportionality constant is H. So this H has now become the famous Planck's constant. Okay, and this is a number like this. So by assuming this, he finally got the correct solution, which we now know that it should be in this form. Okay. Well, this is a complicated equation, so do not remember this. Actually, even though it was correct, I do not want you to remember this. You don't have to. Only just remember that he was correct. So he exactly got this red curve. And then let's simply see how this red curve looks okay. So if you go to longer wavelengths, for example, the lambda becomes infinity, and this part will go to 0, right? And at the same time, if this goes to infinity, you can see that the whole number becomes 0, so it's a pretty small number. So therefore, eventually, this will go to 0. Looks okay, okay? And then how about lambda going to 0? If lambda goes to 0, you see that this part may be going to infinity, but now this is exponential. And if you insert 0 here, exponential of this becomes infinity. And of course, the exponential goes to infinity much faster than this goes to infinity, and this exponential is in the denominator. So therefore, this again goes to 0. So mathematically it's correct. Okay. But then important thing is that Planck, even though he got the correct solution, he didn't he didn't understand why this was correct. Okay. And then later, it took some time for people to realize why it was correct.